My name is Adam Avoian. I've been the team leader on this semester's technology commercialization project working on an Ames National Lab innovation for the recycling of valuable rare earth magnets. Before we get into that, a few thank yous are definitely in order. First to the CCW staff for the opportunity to work on this project, and especially to our fellow Alyssa Boutel for her constant guidance and advice to myself and to the entire team over the course of the entire semester. A huge thanks is also due to graphic designer Megan Nash for her contribution to the design of our slide deck that you'll see tonight. And of course, a big thanks to the fine people up at the Ames National Laboratory, Ryan Ott, Todd Dorkowski, and Craig Forney for their fantastic involvement with our team over the course of the semester, even though we've been separated by distances of several states. And finally, and most importantly, a big thanks to this team. It's been truly a privilege to work with this team this semester. They're four of the most intelligent, talented, and uniquely hilarious individuals I've had the opportunity to work with. They're all going to go on to do great things and make huge impacts in their future careers. And they've also made a huge impact this semester through our work with the Ames Lab and this truly critical technology. Working against the backdrop of intense geopolitical struggles over critical materials and fighting a U.S. market landscape that is incredibly inhospitable to this type of recycling, this team has managed to devise a strategy that can, for the first time, make large-scale rare earth recycling in the United States a viable proposition. And to do that, they've amassed a truly impressive body of knowledge on the rare earths and recycling markets in the U.S. I could talk for a long time and go on and on about how fantastic this team is and the great work they've done this semester, but I think now it's time for me to let them tell you that story. Here's Kiersten, Adam, Brad, and Julius, Team Rare Earth.
This is a neodymium iron boron magnet, and it goes here in a hard disk drive. And even though it's only 10 grams, it comprises 25% of the value of this product. But these magnets aren't just in hard drives. They're in electric vehicles, cell phones, turbines, MRI machines, hundreds of devices we use every day. And the most important part of these magnets are two elements, neodymium and dysprosium, that belong to a larger classification called rare earths. But the global rare earth market is not looking too hot. China controls 90% of the world's production, and mines are being depleted at an alarming rate. And in the face of massive need for the elements inside of these magnets, U.S. e-waste recyclers do not incorporate recovery into their processes. Recyclers are missing out on value sitting at their fingertips and instead throwing it into landfills. But the Ames National Laboratory has innovated a number of solutions, the most promising of them which is rare earth recycling. This semester, Team Rare Earth has worked to commercialize an Ames National Laboratory innovation that recycles NIB magnets. We've done incredible things this semester. We've come up with the first cost assessment for the Ames process, mapped out the only viable solution for large-scale RER, and initiated contact with a licensing partner. The Ames process has capacity to set a precedent for a paradigm shift in U.S. recycling and launch the start of an e-waste renaissance. Hi, I'm Kiersten Strachan. I'm a Chinese and history senior from Houston, Texas.
Hello, I'm Adam Brobson. I'm a mechanical engineering junior from Tulsa, Oklahoma.
Hi, my name is Brad Hulme. I'm a junior petroleum engineering student from Dallas, Texas.
I'm Julius Shen, a risk management senior from Shanghai, China.
Our team leader is Adam Avoian. Our inventor is Ryan Ott. And our mentors are Craig Forney and Todd Dorkowski. First, U.S. e-waste companies fail to obtain value from critical materials. In the U.S., there exists a lagging e-waste recycling landscape. On the whole, only 30% of e-waste materials are collected, and of that, 30% is outsourced to Asia. And less than 1% of products containing rare earths are collected. This is massive in the face of our critical need for these materials. First, technologies of the future, such as windmills and electric vehicles, are all powered by NIB magnets. Existing mines are speculated to run out by as early as 2035. Let's take a look at how recycling currently happens. First, sources such as hard disk drives, cell phones, and vehicles are collected. They're distilled down to metals and plastics, and then other components along with the NIB magnet. The metals and plastics are sold at market price, and the components are disposed of, which includes the NIB magnet. We propose that the magnet be sent through the Ames process to recover pure neodymium and pure dysprosium, which we can sell at market value. This could revolutionize the way recycling works. First, it could reinvigorate the U.S. recycling landscape. by first adding 27% value for just a hard drive. That's an increase of 30% of what recyclers are already gaining. This has a market potential, if we're just looking at hard drives, of $64 million. And this is necessary in order to provide innovations for the future for sustainability. The process, if implemented on its total scale, could satisfy 2% of demand for dysprosium and 5% of demand for neodymium. Now, Adam Brobson is going to tell you why the process is so special and how it stands up to other processes.
Thank you, Kiersten. The Ames process presents the simplest and most efficient method for extracting maximum value from the NIB magnet. It takes as its input the neodymium iron-boron magnet, which is composed of three main parts. The first part is the matrix material, which is typically composed of some common element, such as iron or boron. The second part is made up of the light rare earth element neodymium. And the third part, which is the smallest but by far the most valuable, is made up of the heavy rare earth element dysprosium. Now we can take this magnet and implement it into the Ames process. This process uses molten magnesium in order to extract the light rare earth element neodymium, which can then be sold for $43 per pound. The other output of this process is the dysprosium-rich matrix, which we can then return to the magnesium process at a higher temperature in order to extract the heavy rare earth element dysprosium, which can be sold for $270 per pound. Now this process has three main advantages over its competitors. The first of these is that it can separate neodymium and dysprosium into two distinct streams. This gives added value to the magnet manufacturer by allowing them greater freedom in how they compose their magnets. The second major advantage is that by speaking with experts in the metals processing industry, we have determined that this process uses equipment and operations that are commonly found in smelting industry, allowing a company to easily add it on to existing operations. And finally, Ames has a provisional patent pending on this process in the United States. So anyone who wants to gain value from it will have to license through Ames. Ames is the simplest and the fastest way of extracting value from the NIB magnet. We compared it to several other ways of recycling NIB magnets. The first of these is hydrometallurgy. Hydrometallurgy is defined as using a powerful chemical or acid in order to extract specific elements from the magnet. This is typically found in mining industry in order to extract specific ores from the magnet. Next, we examined molten salt electrolysis, which uses a direct current and a molten salt slurry in order to extract the various elements. And finally, the Ames process, which is defined as a pyrometallurgical process, but with the several key additions we discussed on the previous slide. Now, the first metric we used for comparison was whether or not the process dealt with hazardous waste. The first of these, hydrometallurgy, is well known to use powerful chemicals such as hydrochloric and sulfuric acid, both of which require specialized waste disposal. Now, the other processes avoid this problem by not dealing with these chemicals. The next metric we used was the operating cost of these different processes. Since hydrometallurgy only needs a slightly elevated temperature to operate, it has a lower electric input and therefore a lower operating cost. The next metric we examined was the speed of the different processes. Now, Ames is by far the fastest of the three processes, meaning that it can get the same amount of output with a much smaller scale equipment and an overall lower capital investment. And finally, we examined the ease at which these processes can be incorporated into existing industry. Hydrometallurgy and molten salt electrolysis both require specialized personnel and equipment in order to operate. This makes it difficult to incorporate it into existing industry, while Ames uses equipment and personnel that are experienced in these methods, and therefore it's easy for a company to take this process and put it onto what they're already doing. Now Bradley will discuss how these advantages can be used to gain value from the market.
Thanks, Adam. Now that we know how the process works and its key advantages, let's see who is most ideally positioned to obtain the maximum value from this process. And to do this, we looked at the different industries that have a reliable source of recycled NIB magnet. The first of those is the e-waste recycling market. This market collects the hard disk drives and the cell phones, which contain a small magnet. The next is the automotive industry, which in the hybrid electric vehicle, there's a moderately large size magnet in those hybrid electric motors. The next two, the alternative energy and the medical industry, in the respective wind turbine and MRI magnet or MRI machines contain a very large magnet. We've been able to rule out both of those industries due to the fact that those magnets have extremely long lifespans and therefore would not be a reliable source to be implemented into our recycling process. We have narrowed down our search to focus on the e-waste recycling market due to the fact that hard disk drives provide the vast majority of the NIB magnets that could be recycled. However, in future years, the hybrid electric vehicles and cell phones could provide a substantial add-on. So now let's take a look at the e-waste recycling market and how that breaks down. It starts with the 9 million tons of e-waste that is produced annually in the United States. Only 30% of that is collected for recycling. Of that 30% is exported to Asia, and only 23% is collected by the top 20 companies. This has created a very fragmented market. However, we have primarily focused on those top 20 companies because these companies take in the necessary volume of e-waste to justify the implementation of the Ames process. Furthermore, we have focused on a fully integrated recycling company. And to further explain about what these companies do, let's take a look at the e-waste value chain. It starts by the sources being collected by a metal recycling company, which collect and mechanically break down those sources into the ores. They then sell the ores to the secondary smelters, which then further process and refine those ores into the pure elements, which is then sold to the global magnet market. We have identified that a fully integrated company is the most ideal because they do both of these steps underneath one company. These companies have the access to the necessary sources that we've deemed necessary, and they also some of these companies take in the hybrid electric vehicle motors, which would provide the substantial add-on in the future years. Also, these companies have the necessary infrastructure to easily implement the Ames process, which would allow them to obtain the full value of the NIB magnet. So of the top 20 companies that we had identified, 3 of those companies are fully integrated, being Intercon Solutions, Canadis, and Colt Refining and Recycling. These companies together take in 4% of the recycled e-waste, or 110,000 tons. While we recommend that Ames pursue all 3 of these companies, we've been able to speak to Canadis, both the CEO of the collection and the refining department of their company, and both of these gentlemen have expressed serious interest in obtaining value from these NIB magnets. So now, Julius will talk about how Ames and Canadis will be able to obtain value from this process.
Thank you, Brett. With this defined market and value chain, Ames process will able to increase 30% profit margin for the licensees by each hard disk drive they recycle. Let's look at it. So Canadis collect their hard disk drive from existing sources at 30 cents per hard disk drive. And they produce the pure outputs such as precious metals, plastics to the global market and obtain $1.20 for each hard disk drive. That makes 90 cents profit. And add-on Ames process cost only at 10 cents per hard disk drive, which including the extraction cost for the magnets from the hard disk drives, the operating costs, primarily the utilities, and the shipping costs. And they can make 37 cents more from the rare earth materials they recycled. That makes 27 cents in addition to their existing operation, or 30% profit margin increase. With this great financial benefit of the unique economics, let's look at the big picture of Canada's business financial model. So Canadis were able to obtain $1.7 million accumulated by 2021 based on the following assumptions. First, for cost. We assume the same variable costs as I mentioned earlier, including the extraction cost, operating cost, and shipping cost. And we assume there's no incremental sourcing cost due to their existing collection of hard disk drives. Then we assume the capital investment at $1.1 million compared to a hydrometallurgical process existing that scaled down to Canada's operation level. For revenue, we assume Canada is able to capture 0.2% of the entire hard disk drive market and increasing at 0.05% annually. There are also existing operations, they collect cars. So for the car motors they recycled, we also assume they can capture 0.1% of the market and increase it at 0.05%. Last, we're using the current commodity price for neodymium and dysprosium, and both at the 5-year low, which brings a significant upside potential profit for Canadis and other licensing partners. In totality, by 2021, Canadis can obtain $1.7 million, and Ames National Laboratory, for their 2% royalty, they can obtain $56,000, and break-even can occur within 3 years. With this great financial benefit, there still have several next steps for Ames and the licensing partner to do in order to moving forward the commercialization process. For Ames, they have to negotiate the licensing detail with the candidates and pursue multiple licensing agreements. As Brad mentioned earlier, there are 3 fully integrated recycling companies we research, and we recommend Ames to pursue all 3 companies. They also need to optimize the process, work with their licensing partner in terms of scale up to the industrial scale and verify costs are necessary. For the licensing partners, they need to assess the ability for NIB magnets extraction from the hard disk drives, as well as construct the facility in order to implement the process by 2017. Team Rare Earths are really proud to say that we have this great opportunity to work with Ames National Laboratory and the I-CCEW this semester. And we are proud to say that we performed the first economic evaluation for this technology. We propose a plan for the first large-scale rare earth recycling technology within the US and initiate a contact with a potential licensing partner for Ames National Laboratory. And we are really excited to see where this technology moving forward and make the impact for the rare earth market. Thank you all for coming, and now we open the floor for questions.
So the magnets are currently thrown away for a number of reasons. First, there hasn't been the technology to recycle them in a cost-effective way until the Ames process was sort of commercialized by us. Second, it's currently been a little bit cheaper on a global scale to just buy from China, to buy directly from the ground. But their situation, they're cutting back exports, and also the operations that were planned to open in the US aren't really rolling out as easily as we thought they were. So it previously has been effective to just not have to recycle, but it's becoming harder and harder, so that's why. Okay.
You mentioned that I believe it was only in 5 years Ames could return approximately $50,000. Is that a big enough number for them to go through this entire process and wait 5 years to get that return on investment?
So currently, Ames indicates the interest of just to let the technology out in the market that start the trending of recycling rare earths that can reduce the dependence of China's production. So they even willing to not obtain any royalty at this early stage. So the purpose is just trying to get the technology out and trying to get as much recyclers or companies interested to start the recycling. And by the time you can reach so many different companies, then you can maximize profit at that time.
Why do you need to sell the products back to the globalized magnet market?
Yeah, so the reason that we would recommend that a licensing partner would sell the pure elements output back to the global magnet market is due to the fact that 80 to 90% of the neodymium and dysprosium is consumed in the magnet manufacturing process, and less than 1% of that of those magnets are manufactured in the U.S. So it would be necessary for them to sell those outputs back to the global market. Specifically, we'd recommend that they sell them back to Japan due to the fact that they are dependent on China for their reserves, and they would be able to pay a premium for those elements.
I mean, it's 0.05% because, as Brett mentioned, in the market, it's really fragmented, the market. But for both source of the hard disk drives and the vehicles, the collection part of the CEO of candidates already indicate that they can try to gather just more, collect more hard disk drive, all the sources needed if that unique economics makes sense to them. So it's really small relative to market, but the number is relatively big compared to the percentage. Yes.
So with respect to your sourcing, you mentioned that you're neglecting the wind turbine use and one other very large magnet use, I forget. MRIs, that's right. So you mentioned that that was because they don't go bad very quickly, but since they are so large, would it still be worth it to try and get those magnets back?
Right, so you're correct in that both the MRI machines and the wind turbines have those magnets. Since they're so large, their lifespans are in the 20 to 25 year, and since would not be a reliable source to implement into our process. However, very frequently those magnets are collected for reuse. If the machine as a whole were to go bad, they could either reuse those magnets back into another wind turbine or MRI machine, or break down those magnets into smaller magnets for other purposes.
We're taking one more question.
How did you all account for the decreasing demand for HDDs, for solid-state drives and cloud storage being kind of the future? How can you convince someone that this is something that's worth investing into?
Yeah, so while hard disk drives, the consumption of those magnets and the consumption of the hard disk drives in itself is decreasing, the demand for the rare earths for the production of an ever-growing wind turbine market and also the hybrid electric vehicles market is very large. So we would be able to recycle the hard disk drives that in the future years will become obsolete, and while selling those outputs to the ever-growing demand for the other products.